We will now see how to integrate this given integral, that is integration of x over square root of 3 minus 2x minus x squared dx. I'm going to use this method of substitution. So first I'm going to make the substitution 3 minus 2x minus x squared equals t. So let's use this substitution. Now I'm going to take differentials on both sides. Before I do that, I put a bracket like this so that I take differentials of each of the terms and then multiply it with dx. So differentiation of 3 is 0 and differentiation of negative 2x is negative 2 and differentiation of negative x squared is when you apply the power rule you get negative 2x times of dx. This is equal to, we have the differential dt on the right side. Now I can factor out negative 2 from both sides. So when I do that, I get negative times of 1 plus x times of dx equals dt. Now I'm going to sort out only for x plus 1 times of dx. So I'm going to have only x plus 1 times of dx on the left side. So for that I need to divide both sides by negative 2. When I do that, I get negative dt over 2. So this is what we get after we do the substitution and then take the differential. However, when you look at the given integral, we have only x times of dx. If you look at the numerator part, we have only x times of dx, but we don't have x plus 1 times of dx. So we need to first to recreate this. Let's see how to recreate this. I'm going to make this a little bit shorter and put it over here. So let's have it like this. This is from the substitution. As such, we have seen that we should have x plus 1 times of dx. Since we don't have x plus 1, I'm going to add plus 1 and minus 1 in the numerator so that it does not change the numerator part. So I'm going to add plus 1 and subtract 1 such that it becomes x plus 1 times of dx, and in the denominator I have this 3 minus 2x minus x squared under the root dx. So this could be split into two fractions as like this. I can consider this x plus 1 as one part and negative 1 as another part, divided by, we have the same factor, that is 3 minus 2x minus of x squared under the root. We have this dx. Now this could be written as two parts. So I'm going to write down considering this as one part. If you look at this, this is one part of the fraction, and another part of the fraction I can consider this negative 1 like this. So let me write this. This is x plus 1 over the same denominator, that is 3 minus 2x minus of x squared under the root minus 1 over 3 minus 2x minus x squared under the root whole dx. Now this looks like integration of a difference which is equivalent to difference of the integral. Suppose if you use this formula f of x minus of g of x dx, you have a integral of difference. This is equal to difference of the integral. So this could be written as f of x dx minus integral of g of x dx. So I'm going to use the same property over here, considering this as f of x and the second fraction as g of x. So when I use the integration property, I will get the first part as x plus 1 over 3 minus 2x minus x squared under the root dx. This is one integration, and the second integral is 1 times of dx over 3 minus 2x minus x squared under the root integral. So basically we have got two integrals. We can consider this as integral 1 and we can consider this as integral 2. So let's integrate the integral 1 first. So I'm going to copy this integral 1. I have I1 equals x plus 1 over 3 minus 2x minus of x squared under the root dx. Let's continue with this integral. We have already done the substitution, that is 3 minus 2x minus x squared equal to t. So I'm going to make use of the substitution only for the integral I1, and when I do that I will get, we can also see that we have this factor x plus 1 times of dx. So this could be replaced as negative dt by 2, so which I'm going to do it. So this will be, the numerator part will be negative dt by 2 over 3 minus 2x minus x squared. We could replace that by t. So therefore this becomes root t, and let's further simplify this. So I can rewrite this as a negative 1 by 2 dt over square root of t, whereby I have applied the constant multiple rule. I have pulled out the constant 1 by 2 out of the integral. Now we just have to integrate only the 1 over root t, and this could be considered as t raised to the power of negative 1 by 2 dt. We now apply the power rule, which says that if you have an integral in the form of x raised to the power of n dx, uh, the rule says it is equal to x raised to the power of n plus 1 over n plus 1 plus the constant of integration c. So this is equal to negative 1 by 2 t raised to the power of negative half plus 1 divided by the same component, that is negative half plus 1. I can put the constant as of now it is as c1, because I am dealing with integration 1. I just put the constant as c1. So let's simplify this. This is equal to negative 1 over 2. Negative half plus 1 is this is equivalent to half. So this becomes t raised to the power of half divided by negative half plus 1 is, once again this is half, and we put the constant of integration as c1. Now we can see that these two gets cancelled, and we finally have a negative of t raised to the power of half, which is equivalent to negative of root t plus c1. We will now substitute or do the back substitution for t. Uh, 3 minus 2x minus x squared is t. So we do the back substitution. So this is equal to negative of 3 minus 2x minus of x squared under root plus the constant c1. We will now integrate the I2. So let me first copy the integration I2. This is our integration I2. I'm going to copy it here. So I2 is equivalent to 1 dx over 3 minus 2x minus of x squared under the root. Okay, so to evaluate this integral, first we need to write down this factor 3 minus 2x minus x squared using the completing the square method. So first let's do that. I'm going to rewrite this as 3 minus 2x minus x squared. This is equal to negative of x squared, negative 2x plus 3. I write down in the form of decreasing powers of x. Now I am going to factor negative from this from all the terms. So which means I will get x squared plus 2x minus 3. And when we use the completing the square, we have to take the half of the coefficient of x, add its square and subtract its square. So let's do that. So this will be x squared plus 2x. The half of 2 is, that is 2 divided by 2 is 1. So we have to take the 1 square and we have to subtract the 1 square. So I'm going to put this as plus 1 square minus 1 square, and we already have negative 3. So I put the negative 3 over here. So this becomes, we already have a negative in front. We can now combine these three terms, this is actually the expansion of a binomial x plus 1 raised to the power of 2. So we could put this as x plus 1 quantity squared, and we have negative 1, negative 3, which is negative 4, and this could be written as negative 2 squared. So let me write down this as negative 2 squared. Now I multiply this negative 1 which we have in front. That is basically I distribute this negative 1 to these two terms. So when I do that, this negative 2 will become positive 2 square. So therefore this becomes 2 squared minus of x plus 1 quantity squared. So we can put this over here. So I'm going to replace that over here. So I will have dx over 2 squared minus of x plus 1 quantity square, all this under the root dx. Now this is in the form of integration of some particular function, which means we can apply the formula. So we have the formula dx over a squared minus of x squared. When we integrate this, the formula is sine inverse of x over a plus the constant of integration c. So we can apply this formula over here. Before that, we could also make a substitution so that it gets into this form. So I can do the substitution x plus 1 equal to t. So let me put this x plus 1 equal to, I put u. Now I take differentials on both sides. So this becomes dx equal to du, which means I can replace this dx as du. Let me do it over here. So therefore our integration I2, this is equal to dx is replaced as du divided by 2 squared minus of x plus 1 quantity is u. So therefore this becomes u square under the root integral. Now we can easily compare this form with this formula, where a is replaced by 2 and x is replaced by u, which means according to the integration rule, it is sine inverse of x over a. So when we integrate over here using this formula, this becomes sine inverse of u over a. The value of a is 2 here. So this becomes 2 plus the constant of integration c2. Now let's back substitute the u. So therefore this becomes sine inverse of, we do the back substitution for u equals x plus 1 over 2. Need to put the bracket completely for this. So I'm going to replace this as x plus 1 over 2 plus c2. So this is the result of I2. Now let's combine this I1 and I2. Remember that we have a negative, that is our actual integral IU, if we call this as I, is equal to I1 minus of I2. So let's combine these two integrals. Therefore our final integral is equal to I1 minus of I2. Let's replace the I1. So this is our I1. This is the result of our I1, which is negative of 3 minus 2x minus x squared under the root plus c1. So I'm going to substitute here. This becomes negative of 3 minus 2x minus x squared under the root plus the constant c1 minus the result of I2 is sine inverse of x plus 1 plus c2. So this is sine inverse of x plus 1 over 2 plus c2. Now we can combine these two constants, that is c1 and c2. This could be replaced by another constant c, because when we add these two constants, we are going to get a constant which could be replaced as just one constant. So finally we will have negative of 3 minus 2x minus of x square under the root plus, oh, we have a negative sine inverse of x plus 1 over 2 plus C, where this C is equivalent to C1 plus C2. So this is the result of our even integral. We will now integrate the integral given in part B. So we have integration of x squared times of square root of x minus 1 dx. Once again, I'm going to use the substitution method. So I'm going to put x minus 1 equal to, let's say, t squared. Now I take the differentials on both sides. So I get dx equal to 2t dt. And from this, we can solve for x, in fact, for x squared. So I add 1 on both sides, which gives x equal to t squared plus 1. And when I square it up on both sides, I get x squared equals t squared plus 1 quantity squared. And this is equivalent to x squared is equivalent to, I can expand this using algebraic identity, or I can just foil the term x2 t squared plus 1 multiplied itself with t squared plus 1. So when I do that, I'll be getting t raised to the power of 4 plus 2t squared plus 1. Now we have done the substitution. So we get into our integral and replace all the x as well as the dx. Everything should be in terms of t. So now we have this x squared. This could be replaced as t power 4 plus 2t squared plus 1. So let's do that. So therefore this integral is equal to integral of t power 4 plus 2t squared plus 1 times of, we have under the root x minus 1. So under the root x minus 1 is, we have did the substitution as t squared. So therefore this becomes under the root t squared. And then finally we have this dx. This could be replaced as 2t dt. So let's put 2t dt for dx. Now we have to simplify this and integrate. So let's do that. So this will remain as it is, that is t power 4 plus 2t squared plus 1. And under the root of t squared, this square root and the square term will get cancelled. So we will have only t, t times of 2t dt. Now I can combine these two. These two are like terms. That is t times of 2t is 2t squared. So I'm going to put this as 2t squared dt. 2t squared dt. Now we can do the distribution of each terms, this with 2t squared. So when we do the distribution, we get 2t power 6, because when we multiply t power 4 with t squared, we have to add the powers, that is 4 plus 2 is 6. And now we multiply this 2t squared with 2t squared, we get 4t raised to the power of 4 plus 1 times of 2t squared is 2t squared dt. Now this could be written as a sum of integrals, because we are finding the integral of a sum. So I can write down this as 2t power 6 dt plus 4t power 4 dt plus 2t square dt. Now we can use the constant multiple rule to factor out the constants first. That is, we have 2 here, we have 4 here, and we have 2 here. So all the constant could be factored out of the integral. That means I can write down this as 2 times of integral of t power 6 dt plus 4 times of integral of t power 4 dt plus 2 times of integral of t square dt. Now we have to apply the power rule. That is, if we have x raised to the power of n dx, and the integral of this is equal to x raised to the power of n plus 1 divided by n plus 1 plus the constant of integration. So I'm going to write down this as t integration of t power 6 is t raised to the power of 6 plus 1, which is 7, divided by the same power, that is 7. And I will put this constant of integration as just one constant of integration for the complete integral. So now I move on to the next integral, which is 4 times of integration of t power 4. So once again, if I apply the rule, this will become t raised to the power of 4 plus 1, which is 5, divided by 4 plus 1, which is 5 once again, plus 2 times of t raised to the power of 2 plus 1 is 3, divided by 2 plus 1 is 3, plus I put the constant here, that is constant c. Now we have to simplify this and do the back substitution for t. We know that we have done the substitution, x minus 1 quantity is equal to t squared. So using this we can solve for t. So t is basically, we have to take the square root on both sides. When you do that, we get t equals square root of x minus 1. So we can do the back substitution over here. So therefore this becomes 2 times of x minus 1 raised to the under the root power 7 over 7, plus 4 times of x minus 1 under the root raised to the power of 5 divided by 5, plus 2 times of x minus 1 under the root raised to the power of 3 over 3, plus c. This could also be considered as our answer. However, we could also make it a little bit simpler by rewriting this x minus 1 under the root as x minus 1 raised to the power of 1 by 2. And I'm going to do this. So this becomes x minus 1 raised to the power of 1 by 2, once again raised to the power of 7 over 7. This could be further simplified as so we had to multiply the powers using the laws of exponents. That is, if you have a raised to the power of m and raise it to the power of n, this is equal to a raised to the power of m times of n. So when we use this rule, this could be rewritten as I'm going to write down here 2 times of x minus 1. This is equal to 2 times of x minus 1 raised to the power of 7 by 2 over 7. We remove this. In the same way, I can do the other integrals. So this will become 4 times of x minus 1 raised to the power of 5 by 2 over 5, plus this, the next term will become x minus 1 raised to the power of 3 by 2 over 3, plus c. So either we could consider this as answer, as I uh, already told. This part could be considered as answer, or this could also be considered as the answer. So both are in a slightly different form. However, we could consider one of them as answer to this question.